chair this part of the 2023 MoCaO lectures, which are on polynomial optimisation. And today we have Georgina Hall, who is an assistant professor at INSTEAD in the decision science area, which is she's situated in the campus in France. She received her PhD in operations research and financial engineering in Princeton University in 2018. She was also a Gordon Wu Fellow. Before joining INSTEAD, she held a postdoctoral position in the Diogene team in INRA. Georgina is a recipient of the 2016 Informed Computer Society Best Student Paper Award, the 2018 Informed Optimisation Society Young Researchers Prize, and the 2020 Information Theory Society Paper Award. So she comes with great credentials, and I'm very interested to hear what she has to tell us about polynomial optimisation. So go ahead, Georgina.
Thanks very much, Andrew. Yes, I hope I'm going to live up to those expectations. Very happy to be here. So today I'm going to be following up on what James has been telling you about. So I'm going to be talking about more scalable approaches to sum squares optimization and semi-definite programming. So let me start off with a quick recap of what has been covered so far, just to make sure that everybody's on the same page here. So very briefly, what you've been seeing so far is about non-negative polynomials. So we say that a polynomial p of x in n variables, x1 through xn, is non-negative if p of x is greater or equal to 0 for any x that you plug in. So for any x that you plug into this polynomial, you get something that's non-negative. So here's an example, a univariate example. Here it's quite easy to eyeball it and to think, okay, well, this polynomial is manifestly non-negative. But what happens if you look at a much more complicated polynomial, maybe something that looks like this, that has 3 variables? It's a lot harder to say whether this polynomial is non-negative or not. And in fact, what we're going to be interested in is something that's more than checking global non-negativity of a polynomial. What we want to do is we want to check non-negativity of a polynomial over what we call a basic semi-algebraic set. So you must have heard about these already. So that's one thing we're interested in. And in fact, we're even interested in something a bit more than that. It's not about only checking non-negativity of a polynomial. It's actually about optimizing over the set of non-negative polynomials. So this is what I mean when I say optimizing over the set of non-negative polynomials. I'm looking at an optimization problem of the following type. So here my decision variables are going to be the coefficients of the polynomial p. So we have a polynomial with different monomials, and every single coefficient in front of each of these monomials is going to be a decision variable. So that's the decision variables we're considering. And then we have an objective, which is linear in the coefficients of p. So if the coefficients of p are, say, p1, p2, p3, this is a linear function in p1, p2, p3. And then we have a first set of constraints, which is affine in the coefficients of p. And we have this last constraint here, which is the one that makes it complicated. It's this non-negativity constraint. So on top of requiring that we have certain relationships between the coefficients, certain affine relationships between the coefficients, we're also requiring that the polynomial itself be non-negative for any x within this set. So within this set described by other polynomials, gi, so gi of x is greater or equal to 0 for I equals 1 through m. So we're asking that this polynomial be non-negative over this set here. So here's an example just to get an idea of what this looks like. Again, James has already told you about these kind of problems. So for example, here, if we're considering this polynomial here, so one of the coefficients here is fixed. We're requiring that this polynomial in 2 variables, so c1x1 squared minus 2c2 x1 x2 plus 5x2 to the 4th is non-negative. And we require this for this set of polynomials here. for this set of variables here. And then we have relationships between the coefficients. And our objective is to minimize the sum of the two coefficients. So this is, for example, something that we can see when we're trying to optimize over non-negative polynomials. And a key question is, why would we be interested in problems of this type? So where do problems of this type arise? So James has already given you a couple of examples, this one in particular. So this first application is in polynomial optimization. So if you're trying to minimize a polynomial such that some polynomial inequalities hold, so like what you see here, so minimizing P of x such that Gi of x is non-negative, then you can rewrite this as finding the largest lower bound. So finding the maximum gamma such that P of x minus gamma is non-negative for any x over this set. And this problem here is exactly of the type that we saw before. Here, the polynomial under consideration is P of x minus gamma, and we're trying to find one of the coefficients of this polynomial, namely gamma. So this is a linear objective in the coefficients of this polynomial, and we're requiring that this polynomial be non-negative over this set. And polynomial optimization arises in many different applications. So for example, automated theorem proving. So if you're familiar with the kissing number, which is in R3, right? If I'm talking about it in R3, that's easily, it's easy to explain. Imagine you have a central orange and you're trying to put as many oranges as possible around that central orange, such that they all touch the central orange, but they don't overlap, well, they don't bump into each other in some sense. So that's what is known as the kissing number problem. And for example, you can use polynomial optimization to obtain so bounds on this kissing number in many different dimensions. So economics and game theory is another place where polynomial optimization arises, for example, in polynomial games. Optimality certificates for discrete optimization. So if you want to certify that a certain number is optimal for a given discrete optimization problem like max cut or something like that, then you can use polynomial optimization there. And then maybe a more recently popular application of polynomial optimization is in the optimal power flow problem. So this is a problem in energy. And the question is, if I have a network and I have certain nodes of this network, which are generators, and other nodes of this network, which are sinks, basically how much should I be producing in each node that's a generator to satisfy the demand and in such a way that properties of physics are respected. So this is the first application where optimizing over non-negative polynomials is important, so polynomial optimization. Let me tell you a little bit about this one, which is a personal favorite because it's an application I've worked on, which is more in machine learning and statistics. And the idea here is to do shape constrained regression. So what do we see here? We're trying to fit a polynomial curve to data points. So much like linear regression, instead of fitting a linear map to the points, you're going to fit a polynomial to these points. So the input to your problem is these data points xi, yi. So xi are the features and yi is the response. And so we're trying to fit a polynomial to these data points. And typically there are some properties on the shape of the polynomial that are known. So for example, imagine if you're trying to sell a car and you want to price this car. You would expect, so each car has a certain feature vector. So for example, its mileage, its age, and so on and so forth. And then the response variable there is going to be its price. Now you can imagine that you already know some things about the relationship between the price and some of the features. So for example, if the car is older, so if the age is higher of the car, you would expect the price to decrease. So these are what I call shape constraints, and you would like your regressor, when you try and fit your regressor to these data points, you would like that regressor to actually have that shape. So you want to impose constraints on that regressor. You want to say, I want my regressor, for example, to be decreasing in age, and the age feature, well, requiring this, imposing this, can be formulated in the following way, all right? So you're trying to minimize here. This is just, I'm trying to fit my polynomial to these data points. But then you can impose, for example, a monotonicity constraint in feature xj of the regressor by requiring that its first derivative be non-negative over a certain region. So for example, a box B. And writing this problem down, you obtain exactly the problem that we were considering before, where you're trying to pick coefficients, right? So this is a problem of optimizing over non-negative polynomials. Here the unknowns are the coefficients of the polynomial P, and you're trying to ensure that this polynomial, the derivative of this polynomial, which is again a polynomial, is non-negative over this region. So this kind of problem as well, so shape-constrained regression, fits in to this overall notion of non-negativity of the polynomial, optimizing over non-negative polynomials. That's my second application. And the third application I'm going to go over very quickly. So it's just in control. So for example, trying to certify any kind of properties of a dynamical system is typically can be modeled using, again, this paradigm of optimizing over non-negative polynomials. So you can do this by searching for what we call Lyapunov functions for dynamical systems. So if your dynamical system is this map, right, from Rn to Rn, so it maps the current position to the velocity vector, then you might want to certify, for example, that this dynamical system avoids a certain unsafe region if it starts within this given initial set. And the way you do this is you look for what we call a Lyapunov function, which is a function that maps from Rn to R, and that has the following properties. It's going to be negative over the initial set. It's going to be positive over the unsafe set, and then you require that it decreases over time, and that will guarantee that you will never hit the unsafe set because it starts negative and decreases, so it will never go positive. So this is a way of certifying that you're going to avoid this unsafe set, and searching for this V, if you parameterize it as being a polynomial. So you search for this V as a polynomial, as you can see here. The constraints you have when you search for this V are exactly non-negativity constraints of the polynomial over given sets. And you can require something similar if you're trying to show that an equilibrium point is stable. You can also search for a certain Lyapunov function that has properties of non-negativity over given sets. So these are three applications, and I hope it's given you confidence that optimizing over non-negative polynomials is something that's important if you weren't already convinced by the first three lectures you saw. So it's a pretty fundamental problem, this problem of optimizing over non-negative polynomials. And it has a connection to something called sum of squares polynomials, which is also a concept you've already seen. So very briefly, a polynomial P is a sum of squares if it can be written as a sum of squares of other polynomials Qi. And what's interesting to us is that testing whether polynomial P is a sum of squares can be formulated using what is called a semi-definite program. So there's this connection between sum of squares polynomials and semi-definite programming, and this happens through this following property here. So polynomial P of x of degree 2D is a sum of squares if and only if you can find a positive semi-definite Q. So this is a matrix Q that has non-negative eigenvalues, such that you have this equation between the two. So P of x equals Z of x transpose Q Z of x, and Z of x here is the vector of monomials of degree D. And in other words, if I go back to my initial polynomial that I have here, I can certify that it's non-negative by showing that it is a sum of squares, because a square is non-negative, so sums of squares are also non-negative. So my initial question to you was, is this polynomial non-negative? The answer is yes, because it can be written as this sum of squares decomposition. Or alternatively, you can find a matrix Q here, and I guarantee to you that this matrix Q is positive semi-definite. So you can find a matrix Q that is this one, such that P of x is Z of x transpose Q Z of x. So this enables us, so the problem of optimizing over non-negative polynomials is actually a hard problem, but what we typically do is we replace this problem of this this problem by a sum of squares program. So we use the concept that we just saw here, this concept of sum of squares, to make the problem tractable. So what we do is we replace here this non-negativity condition, which is the one that is painful. We replace it by this alternative condition, which is P of X is a sum of squares polynomial plus a sum of squares polynomials times the GI of X's that you find here. And here, every single polynomial, that's a sigma, so sigma 0, sigma 1 through sigma n, are sums of squares polynomials. Now, it's quite easy to see that if this holds, then P of X is non-negative over this set. So here we have sigma 0 of X non-negative, GI of X, because we're within this set, is non-negative. So the product of these two is going to be non-negative. So P of X overall is going to be non-negative whenever GI of X is non-negative. So essentially, we have this constraint implies this constraint. The question is whether the converse is true. So if the degree of these polynomials is capped to a certain number, which we have to do to have a finite problem here, then the converse is not true. So we lose something here. This sum of squares certificate of non-negativity of P over GI of X non-negative is what is known as a positive Stellensatz. Again, James told you about this during his lectures. It's due to Poutinard in this case. And as I was saying, right, when the degrees of these polynomials are capped arbitrarily to some value, solving the sum of squares program is going to be a semi-definite program, which is tractable, which we know how to solve. So we can solve the sum of squares program you see on the right-hand side. It might not give you the solution to this one, but what it does do is it provides an upper bound on the initial problem. Right, so this is my final recap slide. So here we have our sum of squares program, right, which is this one. So we've gone from optimizing over non-negative polynomials, something which is hard to do, to a sum of squares program, which we can solve using semi-definite programming. And here I'm making the connection between the two explicit, right? So if we're requiring here that P be a sum of squares polynomial, then it's the same as requiring that P of X equals Z of X transpose Q Z of X. This can in fact be written as an affine constraint in the coefficients of P. And we require that Q be positive semi-definite. So essentially here we're going to have a bunch of equalities between the coefficients of P, some numbers, and the entries of Q. And then we have this Q positive semi-definite constraint, which is exactly the format of a semi-definite program. And as I was saying, semi-definite programs are tractable. The issue, though, is that semi-definite programs that come from sums of squares programs typically are very, very large semi-definite programs to solve. So if P has n variables and is of degree 2D here, then this Q, this matrix Q that you see here, is going to be of size n plus D choose D, which is pretty massive. So, and we know, so it's quite well established that semi-definite programs are quite expensive to solve. So if you look at all the sets of convex optimization problems that we know how to solve, this is probably the most expensive class of optimization problems to solve. And its runtime really scales poorly with the size of Q. So a key question here is, can we avoid using semi-definite programming? So maybe can we use a different kind of convex programming when optimizing over non-negative polynomials, and how much do we lose by doing so? So that's going to be the focus of the rest of this talk. So I'm going to be talking about how to replace basically this positive semi-definite constraint by another constraint, by other constraints which are cheaper. Probably, you know, there's no free lunch, right? So probably at the expense of getting worse quality solutions in some sense. So we're going to be trading off conservatism with scalability. So the mechanism to do this is what we refer to as DSOS and SDSOS polynomials. So I'm going to talk to you about these polynomials in part 1 of this talk. And then I'm going to use these DSOS and SDSOS polynomials as my platform to then jump onto more elaborate maybe ways of using these polynomials, which improve a little bit on the conservative bounds we obtain. So this is in part 2, I'm going to be talking about a first method for improving on DSOS and SDSOS polynomials, which we refer to as the basis pursuit method. Part 3, I'm going to talk about an alternative, which is the column generation method. And then finally, in part 4, I'm going to talk about other techniques. So this you can view as one set of techniques to make sums of squares optimization or semi-definite programming more scalable. I'm going to briefly touch upon in part 4 other techniques that can make this happen. So let me get started. If there are any questions, happy to answer them. So let me get started on part 1, so DSOS and SDSOS polynomials. To give credit to who came up with these concepts, so these are 2 researchers who are both at Princeton actually now. So one of them was my advisor, Amrali Ahmadi, and his co-author Arnie Majumdar. So let me tell you a little bit about DSOS and SDSOS polynomials. So this should be familiar to you at this point. This is how we rewrite any sums of squares program. We can rewrite it as a semi-definite program or SDP. So this is how what the SDP looks like, right? And the expensive constraint here is the Q positive semi-definite. So this is the constraint that throughout we're going to be looking to replace. Now, why is this constraint the expensive constraint? It's because this objective is linear in the coefficients of P, these constraints that are affine in the coefficients of P. And then this constraint here, because 2 polynomials are equal if and only if their coefficients are equal, just involves a bunch of equalities involving the entries of Q and the coefficients of P. So really everything else here is linear. So basically the expensive constraint here is the positive semi-definite constraint that's imposed. And the idea that we're going to be looking at in this first part of this talk is going to be, can we replace the constraint, the positive semi-definite constraint, by a cheaper constraint? And I'm going to introduce to you now 2 classes of matrices. So the first class is the notion of diagonally dominant matrices. So you may have heard already of these matrices if you've done a matrix analysis course or something like that. So we say that a symmetric matrix Q is diagonally dominant, and I'm going to refer to the concept of diagonally dominant as DD, if what? If QII is greater or equal to the sum for j different from I of the absolute value of QIJ. So what are those matrices? You take a matrix, right? You look at its diagonal, and you just need to ensure that the diagonal entry is larger than the sum of all other entries on that row, taken in absolute value. So that's what we call a diagonally dominant matrix. It's really the diagonal is dominant with respect to all other entries. And it so happens that there is this implication, which is if Q is diagonally dominant, so we know that matrices that are diagonally dominant are positive semi-definite. So diagonal dominance implies positive semi-definiteness. This is a consequence of a famous theorem called Gershgorin's circle theorem. So this gives us an interesting option, which is we can replace the positive semi-definite constraint here, which was tricky, which gave us this semi-definite program. We can replace it by this condition instead, this diagonal dominance condition. And it so happens, right, that if you're diagonally dominant, then you're positive semi-definite. So we're inner approximating the set of positive semi-definite matrices. And the value of this replacement is that we go from a semi-definite program here to a linear program here, because this condition can be rewritten with involving just inequalities between the entries of Q. So you can get rid of this absolute value is what I'm trying to say. So you can get rid of this absolute value and essentially end up with a bunch of constraints, which are just linear in the entries of Q. So then this becomes a linear program to solve, and linear programs are much cheaper to solve than semi-definite programs. And furthermore, let's say that the technology to solve them is much more mature. So there's been a lot more money invested in solvers for linear programs and so on and so forth. So there's really great techniques to solve linear programs. comparatively maybe to semi-definite programs. So as I was saying, right, the linear programs are going to be much cheaper to solve than the semi-definite programs, but of course this comes at a cost. The diagonal dominant matrices are inner approximations of the positive semi-definite cone. So essentially here we're optimizing over a smaller set. The set of diagonal dominant matrices is smaller than the set of positive semi-definite matrices. We're optimizing over a smaller set, we're minimizing over a smaller set. So we're going to get some trade-off in the quality of the solution in the sense that the optimal value of this problem will always be higher, or will be at least higher than the optimal value of this semi-definite program here. Okay, so we've introduced one type of cone of matrices, right, which is the diagonally dominant cone. And when we contrast it to the positive semi-definite cone that you see here, this is schematic, so we have the diagonally dominant cone, which is an inner approximation of the positive semi-definite cone. Now, the question you can ask is, okay, this is an inner approximation. It might be a pretty bad inner approximation. Maybe it's very small, you know, compared to the whole set of positive semi-definite cones. Can we maybe get something that's intermediate? Because linear programs are very easy to solve. Semi-definite programs are harder to solve in terms of computation time. Can we maybe get something that's intermediate? And the answer to this is yes. And this is given to you via this notion of scaled diagonal dominance. So we say that a symmetric matrix Q is scaled diagonally dominant, or SDD, if you can find a diagonal matrix D with positive entries. So you have your matrix D, which has positive entries, and using this matrix D and multiplying Q on either side, you're going to get something that's diagonally dominant. So essentially here, a symmetric matrix Q is going to be SDD. When you multiply Q on either side by D, you get something that's diagonally dominant. Okay, so what are the relationships between all these concepts, right? So how does diagonally dominant compare to scale diagonally dominant and compared to positive semi-definite matrices? So it's quite easy to see that if Q is DD, then Q is SDD. From this particular definition, it's easy, just take D to be identity, right? And you'll get this, this proof. So we do indeed have that the set of diagonally dominant matrices is inside the set of scale diagonally dominant matrices. So this, so far, so good. This graph is correct. And then it so happens that if Q is scale diagonally dominant, so if Q has this property, then Q is positive semi-definite. So this is, again, quite easy to see in the sense that if DQD is diagonally dominant, then it means that it's positive semi-definite itself. And we know that multiplying by a matrix, a diagonal matrix on either side that has positive entries, this is key, means that Q has the same signed eigenvalues as the initial matrix. So essentially here Q is going to be positive semi-definite because DQD is positive semi-definite because it's diagonally dominant. So we have this notion of scale diagonal dominant cones is the kind of cone we were after, right? We were looking for a cone which was somewhere between the diagonally dominant cone and the positive semi-definite cone. And the scale diagonal dominant cone provides such a set. Oh, I'm going to jump forward a bit. Okay, so essentially what we're seeing here is we can replace this positive semi-definite constraint by two sorts of constraints at this point: the diagonal dominant constraint that gives rise to a linear program, or the scale diagonal dominant constraint, and that we just saw, which gives rise to a second order cone program, or SOCP. Now, second order cone programs, as we'd expect, right, we're optimizing over a set that's a bit more complex. So they're actually cheaper to solve than SDPs, but not as cheap as linear programs. So they give you an improved solution compared to the linear program, but at the expense of something that's a bit harder to compute. So there's really a trade-off going on here. So you have three different levels. You have the LP, the SOCP, and the SDP. These get increasingly costlier to solve. But as a counterpart, the DD, SDD, and positive semi-definite give you increasingly good solutions. So essentially, you're really trading off here the amount of computation time you have against how accurate you want your solution to be. I just want to point out that it's really not straightforward to see that this is a second order cone program from the definition I gave you of SDD. There's an alternative equivalent, obviously, definition of SDD, which makes it much easier to see. And I'm happy to refer you to references so that way you can see that if that's of interest to you. Right, so we've defined these two different sets of cones, well, sets of matrices, cones of matrices. So the notion of diagonally dominant matrices and the notion of scale diagonally dominant matrices, which come as replacements of the positive semi-definite constraint. So the idea throughout, and I'm going to bring this back now to polynomials, is that whenever you see a sum of squares constraint in an optimization problem, so remember that this just involves basically requiring that P is Z of X transpose Q Z of X, where Q is positive semi-definite. This is an SDP. So whenever you see this sum of squares constraint, you can replace it with alternative constraints, which are cheaper. So you can replace this sum of squares constraint by what we call a diagonally dominant sum of squares constraint, so a DSOS constraint. So that just means that instead of requiring that Q be positive semi-definite, I'm going to require that Q be DD. This is a lot cheaper as an optimization problem to solve, because now instead of being a semi-definite program to solve, my sum of squares program, it's going to become a linear program to solve. And if that's not good enough, then you can trade off the DSOS with SDSOS, which is scale diagonally dominant sum of squares. So essentially here you require that your polynomial be not a sum of squares, but an SDSOS polynomial. So instead of requiring that Q here be PSD, you require that Q be scale diagonally dominant, or SDD. So, and this will be an SOCP to solve. Okay, so let me just comment briefly on this. So it's quite clear, because diagonal dominant matrices are PSD and so are scale diagonally dominant matrices. It's quite clear that any DSOS polynomial or any SDSOS polynomial is going to be a sum of squares, and so non-negative, okay? So when you're optimizing over these sets, you're still optimizing over non-negative polynomials, so you keep your guarantees there. But it is a smaller set of polynomials than sum of squares, right? So it is a smaller set of polynomials than the sum of squares, which makes them cheaper to optimize over, but possibly can be of less good quality. So this is the mental map you should have at this point in time. Remember that what we were interested in initially was solving this problem of optimizing over non-negative polynomials. So this is the initial problem of interest to us. This is the one that has all these applications. So it's optimizing over these non-negative polynomials. Unfortunately, the condition that P of X be non-negative makes the problem hard to solve. So there's not much we can do with this problem. But what we can do is we can obtain upper bounds on the true value of this problem by using sums of squares. And this is just, we replace this non-negativity constraint by a sum of squares constraint. Now, if this is too expensive, so essentially now we've gone from something that's hard to something that's tractable, but it still may be expensive to solve, and maybe we don't have the computational power to do that, or we're pressed for time or something. So then we can trade off the quality of this solution with the quality to gain computation time. So we replace the sum of squares constraint by DSOS and SDSOS constraints. This gives us linear programs or second order cone programs. The advantage here is that what we get, the optimal value of the problem that we get here, is still an upper bound on this initial optimization problem. So basically, you know that whatever you're getting here is, you can still say something interesting about it. It's not an ad hoc approximation. You know that what you're getting here is an upper bound, but it might not be as good an upper bound as what the sum of squares problem was giving you. So this is just to illustrate a little bit the quality of these inner approximations on a real example. So here I'm considering the following bivariate family of polynomials. So it's a parametric family. So essentially I'm fixing all of the coefficients of this polynomial, except for these three monomials here, where I'm taking a in front of this term, 1 minus a in front of this term, and b in front of this term. And in this graph, I'm plotting the values of a and b, for which this polynomial is a sum of squares. So this is in blue. So you see all the possible values of a and b for which this family of polynomials is a sum of squares. In this specific case, so with this degree and with these amounts of variables, we know that sum of squares and non-negativity are equivalent. So the set of a and b such that this polynomial is non-negative is also the set of a and b's for which this polynomial is a sum of squares. And inside, we've plotted the set of a and b's for which this polynomial is s d sos. And then in light blue here, d sos. So you can see that, you know, depending on which direction you optimize in. So for example, if you're optimizing in this direction here, then if I look at the optimal point, it's somewhere around here, which is a point where sums of squares and SD sos and D sos polynomials all kind of line up. So you'll be getting a very good quality solution, whichever set of polynomials you use. Now, however, if I'm optimizing, say, in this direction here, the optimal solution that I would get using sum of squares is somewhere here, SD sos is somewhere here, and D sos is maybe, I don't know, somewhere here. So there would be a big gap in the quality of the solution that you obtain. So there's not always this guarantee that by using D sos and SD sos, you're going to get a good quality solution. So that is maybe the main limitation of D sos and SD sos. And this is what the next couple of slides address. So when you replace sums of squares polynomials by D sos and SD sos polynomials, what you're always going to get is faster bounds because you're using, you're solving much cheaper conic optimization problems. But the trade-off you're getting is obviously you're not always going to get as good quality optimal values compared to sums of squares. So the idea for the next two methods, and it's going to be brief, is how can we start from this particular optimization problem? So we start with maybe what can be a poor solution, but then how can we improve on it iteratively by staying within the realm of linear programs and second-order cone programming? So the idea here is that instead of solving one semi-definite program in one shot, we're going to solve many linear programs or second-order cone programs. So the hope here is to bridge the gap between the quality of the solutions we obtain while still remaining in the realm of something that's much faster to solve. So we're going to be iteratively constructing a sequence of improving LPs and SOCPs. So the process is always the same. We start with the D sos as D sos polynomials as our initial problem that we solve. And then we improve on them using one of two methods, and I'm going to describe both methods. So the first method is the basis pursuit method. The second method is the column generation method. So let me start first with the basis pursuit method. So this is work jointly with my former advisor, Mario Mardi. So this is work I completed during my PhD. So let me tell you a little bit about the basis pursuit method. And as you see, it's quite short, so just 3 slides on this. And the key idea is really encapsulated here in this example. So if you take a look at this polynomial should be quite familiar at this point. It's the one that I was showing you at the very beginning, and I was asking you whether it was non-negative or not. Now, we saw in one of the previous slides, right, that it is non-negative because it's actually a sum of squares. So you can write it as P is Z of X transpose Q Z of X, where Z of X is the vector, this vector of monomials, and Q is positive semi-definite. So this Q here is positive semi-definite, but it's clearly not diagonally dominant, right? Let's take a look at this first row. If I sum up all the off-diagonal entries, so 3 plus 1 plus 2, that's much larger than 1. So this is not a diagonally dominant matrix. However, if I just allowed myself to change my basis slightly, so I wasn't using the standard basis of monomials, right? I was using a different basis of monomials that is given here, then in that particular framework, we're using that particular basis of monomials, my polynomial can actually be written as the z tilde transpose x q tilde z tilde of x, and q here is diagonally dominant. In fact, it's actually diagonal. So in other words, if I had access to this basis off the bat, then I would be able to certify non-negativity of this polynomial using just diagonal dominant matrices. So in other words, if I had the right basis, right, I would be good to go. So the whole idea of the basis pursuit method is to go from the standard basis to the right basis in some sense. And how are we going to do that? So we're going to iteratively improve on the initial basis z of x. And how do we do this in practice? So let me walk you through the algorithm. So again, it's an iterative algorithm that solves linear programs or second order cone programs at each iteration. So we start off with the sums of squares problem, which is a problem we don't want to solve, right? Because it's an expensive problem to solve. So we don't want to solve this. We want to instead replace this problem by a sequence of linear programs or second order cone programs to solve. So this is the equivalent, right? Definition of our sums of squares problem. And we're not going to solve this. We're going to replace this condition, this positive semi-definite condition, by a diagonally dominant and scale diagonally dominant condition. So this is how we're going to initialize our method. So we're going to start off by solving this. This is a linear program or a second order cone program to solve. So far, so good. So this gives us an initial solution, which we refer to as Q star. So we're going to get an optimal solution here, P star, Q star, and we're going to use Q star in a smart way. So what are we going to do? We're going to take the optimal solution here, Q star, and we're going to call U1 the Cholesky decomposition of Q star. Now, you don't really need to know what the Cholesky decomposition is. It's just that the only thing you need to keep in mind is that the Cholesky decomposition of Q star is such that U1 transpose equals Q star. And this always exists, and it's quite easy to show if Q star is positive definite. Okay, so we have U1 here. And this U1 is going to give us what we call our new basis. So what are we going to do? We're going to replace the initial z of x that we had here by U1 z of x. This is our new basis. So we're iteratively improving on our basis of monomials at each iteration. And we're going to now require step 2 that P of x be z of x transpose U1 transpose Q U1 z of x, and Q is still dd and sdd. Now, what do we know here? We know that we're bound to recover at least the optimal solution to the previous problem. Why? Because if I take Q equals identity, I'm getting U1 transpose U1, which is exactly from the definition of a Cholesky decomposition, which is exactly U1 transpose U1 is exactly Q star. So I'm going to be recovering here the solution to the previous optimization problem. But of course, I don't need to take Q equals identity here. I can take something much nicer, much better. So basically, I'm going to improve at each iteration by giving myself the freedom to not take Q equals identity, but to take Q maybe Q diagonally dominant or scale diagonally dominant. And then I repeat the process. We keep going, right? So when we get a Q star here, we're going to define U2 to be the Cholesky decomposition of this whole thing here. And we're going to solve here with U2 z of x as our new basis, and so on and so forth. So this is just to give you an idea of how well this method performs on a small example. So we're back to our parametric family of polynomials that you see here. And this is the set of A's and B's for which this polynomial is a sum of squares. This is the set of A's and B's such that this polynomial is a DSOS polynomial. And then this is just one iteration of this Cholesky method. You can see how much it grows that set in just one iteration. And it's even more noticeable here with SDSOS, where essentially one iteration of this process, so just allowing yourself one extra step, essentially enables you more or less to recover the set of sums of squares polynomials. And here is a quick graph, right? When we're trying to minimize the degree for polynomial in 4 variables, this is the kind of bound I would get with a sum of squares bound. So this is my sum of squares bound here, which is around -1.4. And if we start with SDSOS here and DSOS here, then essentially we're starting quite low compared to that minus 1.4. But as we allow ourselves more iterations of this change of basis method, we quickly converge to the lower bound given by the sum of squares polynomial. Okay, so that was the first method, which we refer to as the change of basis method. Now, let me tell you about the second method. Again, it's going to be quite short, which is what we call the column generation method. So it's another way of taking an initial approximation by DSOS and SDSOS and improving on that in an iterative way while staying within the realm of linear programs and second order code programs.
iPad 그리고 이따 비디오를 좀 클릭 있어.
Mama should keep playing.
I think I can hear someone. Let me just mute. Okay, all good. If you have any questions, please let me know. Okay, so yeah, so this is another iterative method to improve on semi-definite programs. So I'm going to focus here on the LP-based method. So I'm going to just talk to you about DSOS and not SDSOS, but it's quite easy to see how this would generalize to the SOCP-based version. So again, this is our initial problem that I'm not going to want to solve because it's too expensive to do so. So I'm going to replace initially with the constraint that PB is sum of squares by PB DSOS. And so this is a linear program now to solve. And it's equivalent, as we've seen, to requiring that P of X be Z of X transpose Q Z of X, with Q being diagonally dominant. Right. So now I'm going to have to tell you a little bit about two different ways of characterizing QDD. So the first definition, which is the one I gave you so far, is that Q is diagonally dominant if and only if we have this property on the diagonal compared to the sum on all the rows. Now, that's one way of defining it, but you can also define it in another way. So this is kind of like a facet inequality kind of definition, and this is more like a vertex kind of, you know, it's the vertex kind of description of this polyhedron. So Q is diagonally dominant if and only if you can find non-negative alpha i's such that Q is this conic combination of VI transpose of all these rank 1 matrices. So essentially Q, you get it by taking conic combinations of these rank 1 matrices. And VI here is going to be a fixed vector with at most 2 non-zero components equal to plus or minus 1. So essentially this Q that you see here is the conic combination of some very specific and quite sparse, as you can see, some very specific rank 1 matrices. And the key idea that we're going to be using here is that we're going to start off with this specific set of rank 1 matrices, and we're going to be adding to it in each iteration. So at each iteration, we're going to be adding an extra rank 1 matrix that we allow ourselves to include in our set of descriptive matrices. Okay, so let's go over this now with polynomials, right? So we have P of X is Z of X transpose Q Z of X QDD, which is equivalent using my second definition here to this. So I can write it in exactly the same way. I'm just requiring here that P of X be sum of alpha I VI transpose Z of X squared. So here VI is my set of rank 1 matrices, right? So this is what gave us the rank 1 matrices we had before. And alpha I is non-negative. So the idea behind the algorithm, as I was saying, is that each iteration, you allow yourself a new square, basically. You allow yourself a new vector V and a new variable alpha, such that P of X is the sum of the initial term plus the sum of a new term. So obviously, you can see that I can recover the previous problem by simply setting alpha is equal to 0, but I can do better because I allow myself to take alpha non-negative. And the key question here really, because alpha I and alpha are variables, right, decision variables, is how do we pick V? How do we pick V in a smart way such that we're guaranteed to improve at each iteration? And the key idea here is to use the dual. So I'm going to just talk about this at a very high level as, you know, as the P and LP duality. But it's quite easy to see how it would apply here in the setting of polynomials. So we have our general SDP here, and we're inner approximating this SDP by the set of GD matrices. So the set of X's that can be written in this way, where the alpha i's are non-negative. And here the X, so this, if we choose our VI's in the previous way, X here is diagonally dominant. So we're in approximating set of PSD matrices by the set of diagonally dominant matrices. Now there's a dual picture to this. So for every optimization problem you see here, there's an associated dual. So the dual of this SDP is given here, as you can see it. And it's just maximize B transpose Y, so the B comes from here. Y is my new variable such that C, which is the matrix that appears here, minus the sum of YI is positive semi-definite. So this is the dual of this SDP. And the dual of this LP is now going to be an outer approximation. So things flip, right? So this before was an inner approximation. Now it's going to be an outer approximation. And what is that outer approximation? We're requiring that VI transpose this matrix VI be non-negative for any I in this set. So essentially, we're not requiring that this matrix be PSD. We're requiring that this product be non-negative for some specific VI's, which is different from being positive semi-definite, because this would be for any VI. So basically, so the dual of this LP, right, will contain, so because it's an outer approximation, we'll have V's for which V transpose C minus sum of YI AI V is negative. And if we want to go towards the SDP, the dual SDP, then we'll just pick a V such that this inequality is satisfied. So essentially, we're going to be trying to go towards the setting where this matrix is positive semi-definite by adding an inequality that's violated currently. And we can show that we have convergence of this kind of method. So if at every iteration we pick V to be the most negative eigenvector, the dual matrix, then this column generation method eventually recovers the sum squares bound. So if you do it long enough, right, this method, then you end up getting the correct bound. And this is a numerical example for you to see. So here we're minimizing a degree for a polynomial, and we're scaling up the number of variables in this polynomial as we go. So from n equals 15 to n equals 40, as you can see, right, in some regime, for example, n equals 30, we're unable to solve the sum squares. The sum squares optimization problem is just too big. It takes up too much memory. We cannot do it. On the other hand, we can still solve our methods based on the DSOS and SDSOS. So here we're just giving DSOS and DSOS K, right? This is this is the initial one-shot approximation. As you can see, it takes very reasonable time, 7 seconds here, 10 seconds here. And we get minus 36.52, for example. So if you compare, for example, at n equals 15, you get minus 10.96, which is a worse lower bound than minus 3.26. So you're not doing so well here, but you can allow yourself to keep improving using this iterative method. So as you increase the number of iterations, so here we cap our time at 600 seconds, you can see that, for example, you can halve maybe that bound that you had initially. So this is the advantage of such a method. Okay. So this brings me to the end of this second method. So we've seen how DSOS and SDSOS polynomials can be used as replacements of sum of squares polynomials. We've seen that sometimes they're quite conservative, these two methods. And so I presented two iterative methods that build on top of these concepts to bridge the gap between the conservative bounds we're getting with DSOS and SDSOS compared to sums of squares, while still remaining in the realm of linear and second order cone programs to solve. Now, let me just tell you very, very briefly, this is literally one slide, about other techniques that can make sums of squares optimization or semi-definite programming more scalable. So what we just saw is a general purpose approach that trades off scalability with conservatism. So essentially, you pay a price, right, for being able to scale up your problem more, and the price you pay is the quality of the solution you get. So that's what we just saw. But there are other ways as well of speeding up the scalability of semi-definite programs. So one way is using basically knowledge on your semi-definite program. So special structures of your semi-definite program. So if you have any of these, so for example, if your semi-definite program has a lot of symmetry in it, or it's a very sparse semi-definite program, or it's what we call degenerate, then you can use these characteristics to reduce its size and then make it easier to solve. If you know something about the semi-definite programming solutions you have, so for example, if you know that the solutions to your semi-definite program are low rank, then you can leverage this to reduce computation time and storage space of your matrices and the SDP solutions in general. So essentially, these are three different ways of speeding up semi-definite programs. And you can also use alternative, cheaper algorithms to solve semi-definite programs. So traditionally, semi-definite programs have been solved using interior point methods, which can lead to very dense sets of computations and everything. If you work with first order methods, this can be much cheaper. So essentially, these are an array of tools to use if you're looking to solve semi-definite programs or sums of squares programs. This is an array of tools you can bring out, and they're all quite complementary, right? Because you can see that maybe your SDP has special structure, leverage that, get a smaller SDP that's still not feasible for you to solve. It's too large, it's still too large. Then you can maybe use the techniques I've talked about here to make it, to solve it approximately, and so on and so forth. So these are really all like plug and play and very modular with one another. I'm going to refer you to this survey that we wrote with Arnie and Amrali on how to use high level recap of how these different methods work, and you'll find references on how to use every single method that I describe here in this survey. Right, so what did I discuss today? So overall, I spent most of my time talking about the fact that optimizing over non-negative polynomials has many applications. So unfortunately, they're hard to solve, right? So we replace the non-negativity constraints by sums of squares constraints. Unfortunately, they're still quite expensive to solve because they rely on semi-definite programming. And what I did here was I presented more scalable versions of sums of squares, which are based on iterative linear programs and second-order cone programs. So two methods in particular, the basis pursuit method and the column generation method. I'm going to stop here because it's exactly 10 a.m. Thank you very much for listening.
Thanks very much for that, Georgina. That was really, really interesting.
Perfect.
So we usually have a few minutes for some questions after this. So we'll now call for questions. So is there anybody? I mean, I have some questions, so I'm happy to ask those first. But is anybody got some questions at this point? If you have questions, please unmute yourself and ask them or put them in the chat. I'll just begin, Georgina.
Yeah.
This goes back to a question actually I asked. Well, actually, first of all, I've asked you provided two methods. Is any one actually better, or are they just better on certain problems? And I mean, is there any comparison made between the two methods you've made? And is one better than the other, or they're just complementary?
No, that's a great question. So I don't have a theoretical answer to bring to you on this point. So a couple of things. So for the column generation method, we have a proof of convergence that actually converges to the sum of squares bound, right? Which is something that we might view as desirable. But interestingly, despite the theoretical guarantees on the column generation method, which we don't have for the first method, the change of basis method, we don't have those guarantees, but in practice, the change of basis method seems to work much, much better than this column generation method. So we don't really have an explanation for that per se, but it just is in practice our observation. Okay.
All right. Just another thing that popped in my mind when you were going through this. I mean, you show that these second order cone problems arise out of your you know, your scalable,
Yes.
you know, techniques. Is there some sort of equivalence between second order cone problems and those formulations? Are they kind of equivalent problem sets?
So this scale diagonally dominant matrix kind of thing?
Yeah, can you, if you took a second order cone problem, could you make it a scalary dominant sort of thing?
Yeah, so
vice versa?
no, so there's subset of second order. I don't think any second order cone program can be written in this way.
Right.
So it's one direction, if you will. So requiring that Q be scale diagonally dominant gives you a second order cone program, but not any second order cone program can be written in this way.
Oh, okay. No problem. That's interesting.
Thanks very much. Yeah, great questions.
The other thing, actually, this is a question I posed to James when he was giving one of his first talks there, is that you know, one thing popped to mind when I first saw this is that, you know, these programs provide bounds, and so you're really developing a bounding function, and in a way, what you're doing with some of these techniques is you're trying to leverage that bounding function through some iterative method, you know, and of course the place where that happens most often is in integer programming, where you use branch and bound, and of course,
yeah,
positive semi-definite programming, you know, you can model at least binary problems, you know, with quite easily with these things. And has anybody done any attempt to use some of these techniques, and maybe in combination, to strengthen a bounding function and then put it in branch and bound to try and develop a technique to solve binary problems, for instance?
Yeah, no, so that's actually a very relevant question, because this second project, so you know, in the two methods I presented, so this is in the third part I was presenting here the Cholesky method, the column generation method. So actually even the name comes from integer programming. So essentially the third collaborator we had here, Sanjeev Dash, he's actually an integer programming person, and he was looking exactly for that. So he was looking for a way of using of how to strengthen the bounds you get in branch and bound at each, you know, branching step, like how can you strengthen those bounds? And the idea was to develop a methodology which didn't involve actually, you know, the whole sums of squares kind of techniques, which just involved something a bit cheaper to do at each iteration. So that's essentially how the project started, was exactly for that, to do integer programming. And I believe that he ran some simulations on his side to see how that performed on in a branch and bound solver. Can't recall, unfortunately, the kind of results he was getting, but certainly the motivation was definitely there.
Yeah, I mean, even with your L, you know, the one which is equivalent LP, I mean, you could use that as a bounding function.
Exactly.
You know, and that could even fit into a normal branch and bound, you know, process. You just augment it with that. In a sense, it's like a you know, what do they call it? A branch and cut, if you like, but your cut is coming from the reformulation.
Yeah, exactly.
Yeah.
No, so that was definitely a motivation for this project. So yeah,
Interesting. Just one last question, if I may, if there's nobody else asking questions. Just out of interest, I mean, when it comes to sort of the modeling power of these things, I mean, you did to give some sort of economic examples, and one problem class, of course, is utility function fitting, and they often, when you're dealing with you know, economic models, you have, you know, various, you know, postulates about the structure of these functions you're trying to fit to data. I mean, have people used these techniques in that area?
Yeah, absolutely. So I can refer you actually to quite you know, selfishly to my own paper, but
okay.
so essentially in this let me show you. So this particular setting, right? I'm just having to go back too much. So in this particular setting, I gave it in a machine learning kind of context, but you can imagine that you want to fit a utility function, right, to some data points, and you want to impose some kind of shapes on that utility function. So concavity is one, right? Like that's typically what we observe for utility functions. And so
you might have some sort of homogeneity kind of assumption as well.
So so you can put that as part of your structure of your polynomial. You can impose concavity, you can impose like it has to be increasing, and all these kind of things. And this you can do. So in this paper, we have an example which is a utility function, like an economics example with a production function actually. And we show that it beats out, there's all these methods that have been developed in economics that actually are suboptimal compared to what can be done. So that's what we show in this paper. So yeah, that is something we've done. We don't use the DSOS and SDSOS techniques. We use like sum squares, like straightforward sum squares there. But yeah, if economics is of interest, I'd recommend taking a look at that example. I think it's
okay. Great.
Yeah.
Okay. Are there anybody else like to ask some questions? No questions? All right. Well, I've exhausted my questions, Georgina. So
it was great to do this.
Yeah, thank you very much. I thought it was a lovely talk, and I learnt several things. So that was enjoyable. Yeah.
Awesome. Okay, great. Well, thank you very much. And yeah, wishing you a good end of your evening, I guess, huh? In Australia.
Yeah, that's right. I suppose it's morning time for you over there at this point. Yeah.
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 Okay.
Okay. Let's thank Georgina for a great talk, and wish her the best for the rest of her day.
Thank you.
Good. Thanks, Georgina.
See you. Bye.
Okay. Bye-bye.